Let's go and practice for the what we say. We will depend in our study or sequential generation on three type of sequences. The type 1 is called B0. The type 2 or the needed second sequence is called diffusion weighted imaging. And the type 3 is called an ADC, which is apparent diffusion coefficient. Let's agree first of all, the two sequences are real sequences. We do it by application of a type of MRI sequence, and we get result. We can control, we can manipulate the parameters. The third type, which is the ADC, it is not a real MRI sequence. Let's agree about this point, which is very important. ADC is an artificial, mathematically calculated type of sequence that we got it from combination of the first sequence, which is B0, and the second sequence, which is diffusion weighted imaging. So it is not a true sequence, it is a mathematically generated sequence. Okay? Let's start with the B0. B0 is a spin echo sequence followed by multiple gradients, which means it is an ecoplanar sequence. Ecoplanar sequence, by definition, is a multi-sequential imaging that starts with spin echo. We give a 90-degree pulse, or excitation pulse, followed by the 180-degree refocusing pulse, and followed by the echo or signal at a certain time, which is T. Okay? After we give this sequence, we give frequency encoding, phase encoding, and gradient sequences to enhance the echo and to also enhance plotting the signal on the K-space and computer. We want a very rapid and short sequence to achieve the result which is noted. Why this is markedly needed? Because diffusion is highly affected by motion. So motion of blood within vessels will affect the result of accuracy of diffusion by total result or by the end result. So we have to do the examination in a very short time, sequential imaging. This is mandatory to achieve a normal or accepted or accurate result of diffusion imaging. Okay? We will not go for long procedures. Okay? So we depend on ecoplanar type of imaging. You will see that when we go for the diffusion, we'll further accelerate the time and shortening it more. This type of image is a T2 star image to start with. B0 is a T2 star image. Why? Because it depends on the gradient and the spin echo and marked early rapid dephasing of spinning protons, as we remember in the previous lectures. So the result is a T2 based, which we call the mother of the diffusion study. The mother of the diffusion study is the T2 study. Okay? The basic sequence of diffusion image is T2 study. You remember when we talked about the inversion recovery, the mother of the study is T1. Okay? When we talk about the gradients, the mother is T2 star. Now we are talking about T2 again, star and T2 baseline of our source of image. So we got this image. Criteria of T2 is present in this image. Fluid is high signal, less gray signals are due to, and we can summarize the point in long decay gives us the bright signal, and early or short decay gives us the dark signal. Okay? This is the basic study, we call it the B0. Now we go for the second needed sequence. What actually we need in this sequence is to suppress the bright signal that is seen on T2 and T2 star. Okay? We have to suppress the brightness Why? To accelerate or enhance the pathological aspect of the disease. We are looking for brightness due to diffusion restriction. Okay? So, in this case, we need a further, stronger gradient application on the B0 to make more dephasing, rapid dephasing, and loss of signal. You know by default, as a fact, dephasing means dark signal. Rephasing means a bright signal. We agree about this point. So the aim of our application of a very strong gradient in this sequence, particularly we call it the diffusion imaging sequence, is to get a dark signal by rapid dephasing. So you notice we add a new sequence or a gradient which is called the diffusion gradient to our initial signal or sequence which we make the T2 start by it, which is called the B0. This type of diffusion gradient is highly potent gradient. Let's give you numbers. The usual gradient is, the strength of it is about 3 to 5 millitesla per meter. The diffusion gradient is 30 to 50 millitesla per meter per second, or per meter, okay? Millimeter square per meter. The time for the normal gradient that we use in gradient sequences is about 3 to 5 milliseconds. The time in diffusion gradient is about 20 milliseconds. So we are really talking about a very strong gradient. Why? To achieve a very strong dephasing and very strong loss of signal. We will make the signal in diffusion images darker. If you compare it with the previous one, the CSF in the ventricle is bright. By applying this sequence, it becomes dark. All the gray matter and the surrounding tissue of the parenchyma of the brain appear gray compared to, they achieve a loss of signal. Still, we are having this high signal in the surrounding of the brain convexity. Why? The answer is because we are basing our study on top of T2. T2 is the mother of the sequence, so there is always contamination of the sequence by the mother sequence, which is T2. But there is element of brightness, although we achieve the strong dephasing. Let's go for our critical point. Critical point, before that, let's identify the B value. B value is measured according to the information of the diffusion gradient. The B value is affected, B value is the distance of time between the first gradient and the second gradient. If you were asked what is the B value in diffusion images, you know that we apply two subsequent gradients per one image or one sequence initiating the ABC and diffusion images. The distance between the first gradient and the second gradient is the B value. The results depends on how much the distance we got, how much the strength of the gradient itself, how much the duration that we apply the gradient. Three factors affect the B value: distance, in time, and the strength of the gradient itself, and the duration that we apply the gradient. If you notice, we apply the gradient before the 180 pulse and after the 180 pulse. These are equal gradients. They should be equal in size and the duration. What will happen if we are talking about two types of tissues? The free diffusion tissue and the restricted tissue. The free movement tissue, which is represented by this first image adjacent to the W diffusion weighted images, we apply the first gradient. This is the first gradient, and this is the first direction of gradient, as you remember, and we can manipulate the gradient in direction and orientation. The freely mobile protons or molecules continuously are moving. Okay? So the first will produce dephasing, which means part which is adjacent to the gradient will move faster, the part which is away from the gradient will move slower. So we are making inhomogeneity and dephasing. Okay? Then we apply the 180. 180 will work as a rephasing component, strong rephasing component. Okay? If we apply the second gradient of diffusion after the 180 and the tissue is in phasing state that will give a signal, we are markedly dephasing the tissue, and the tissue already is not in a equal distance, they are keep movement, so we can't control the effect of the second gradient on it. So dephasing will happen, we can't put them regular and connecting together to produce a signal because of their motion. We are losing signal further due to the second gradient, and we are left with a dark signal. So by application of this, we are achieving marked dephasing due to the continuous movement of the particles which are free. We can't regulate to keep, this is fast and this is slow and collect them in one area to give a signal. So the result is loss of signal due to this gradient in regard to the free movement particles. Let's go to the compact particles or the limited sequential or type of tissue, which is, I think we can call it by now restricted diffusion. What will happen there? What will happen there, the movement of particles almost neglected in this subject. Okay? No effect, remind and memorize this point, no effect of the first gradient or second gradient will happen on the stationary phase of the inflamed or affected or pathological tissue. So what we are left with in the second tissue is a rephasing, keep in phasing due to 180 pulse, and we are having a high signal. The tissue is not responding to dephasing, and so are we having a high signal. So we are left by this sequence with marked loss of signals for the free diffusion and marked bright signals for the restricted diffusion, and this is what we want. You understand the idea?
Yes.
Stationary particles do not respond to the gradient due to stationary position, and what will happen is just having almost high signal due to the refocusing 180 pulse, which doesn't affect the diffusion capability. Motion particles will be affected and go into marked dephasing phase, which is loss of signal, and this is achieved by this brilliant, let's say, technique to accelerate the dephasing and loss of signal. This is the result. We talked previously, this is not enough. We have to combine the DW weighted images with the mother image. This is a computer function. We merge them together. We try to eliminate T2 effect from the diffusion images and remove contamination of the T2 images by computer work from the DW images, and the result is the true evaluation and calculation of the diffusion, and we can apply this to the computer and get our ABC
map.
Okay?
Yes, sir.
Already we give the computer the informations that the diffusion is represented by high signal and restricted diffusion is represented by low signal. The computer will study these informations and calculate and give us the resultant lower ABC. Okay? This is the basic physics of the diffusion images.